This session will discuss about these photodetectors. All we know the importance of photodetectors, right? Because they are used in very small appliances to large things, like starting from automatic door opening in a supermarket to your TV remote, or whatever the video conference we are doing it now, whatever the camera we are using, it's a photodetector, right? And also nowadays this smart cars are coming up in the market. Already they are in the this self-driving cars, where the car drives without any driver, without any assistance. Those cars are basically based on lidar, light detection and ranging. So again, it's a photodetector. So the importance of photodetector in daily life, you name it, everywhere you will see it. Starting from your cell phone to any gadgets, almost there will be some in some form of photodetectors. So if you see their construction wise or the way they work, we can categorize them into few types. Like broadly, let me just write it over here so you can take a note. So we are talking about photodetectors. So broadly they are categorized into two types. One is photoemissive type and photoconductive type. So if you just do a flow chart, so one is our photoemissive, we'll come to that, and then other type is photoconductive. So as the name suggests, photoemissive, it's like we'll have something emission in this type of detector. We all I hope we know about this detector called PMT, photomultiplier tube. This is again a photodetector, and it worked in this photoemissive type, wherein we basically multiply the number of carriers in the process of multiple emissions. We are not much interested in this part in this particularly course, this PMT, but we will focus on other type, where is the photoconductive type, wherein most of the devices are based on semiconductors. So again, the photoconductive types we divide into three broad categories. Three popular types of device. One is our regular photodiode, and then we have phototransistor, and at the end we have photoconductors itself. So okay, so conductors. So let me just briefly tell about something. So photodiode, as the name suggests, it's a again PN junction diode, right? So if you again they are popularly divided into two types you will see in the market if you want to buy a photodiode. So one is normal APD, it's a Avalanche photodiode, and then we have one more type called PIN photodiode. We'll discuss about it, PIN photodiode. Then we have phototransistors. It's a BJT only, but it is sensitive to photons. And then we have photoconductors. Photoconductors we have already used in our experiments. That LDR we use light dependent resistor, so that falls in this category, LDRs. Okay, now we know the broad categories of the photodetectors, so let's have a look at their various parameters. So so we're looking at few important parameters. Okay, so first one is we always look for a quantum efficiency of a device, right? We have already discussed this thing about when you talk about LED, or even in laser also we discuss about this, right? The quantum efficiency. So the first one is quantum efficiency, which is denoted as zeta. And then another important parameter is responsivity. Responsivity, which is denoted as R, and then we have another parameter called transit time, or call it as raise time. Raise time, which is denoted as TR. And then at the last, talk about signal to noise ratio. So it's SNR, S by N, or signal to noise ratio. So these are the few parameters we look for in a photodetectors. So briefly, let's see how we define the quantum efficiency. It's very similar to an LED. So in an LED, I mean, it is exactly opposite. So LED, we had a device, right, wherein we supply for electricity or electrons to the device, and it gives us photons, right? And in this particular type of device, photodetectors, we supply photons to the device and we extract current or electrons out of it. So the working is exactly opposite to each other. So let's just write down its formula once. We know already, just you have to reverse it. So the efficiency, we are talking about quantum efficiency eta. So it is basically so you are generating carriers here, right, or electrons. So it is carrier generated per unit time for okay, it's per unit time for the photocurrent for the photo current or photon flux also you can say. And and our input is, so this is basically the output from the device, and the input is our incident photon flux, right? So this is incident. It's exactly opposite if you remember the working of an LED. So if you write it in equation, so it will be IPH photocurrent by, if you divide with electron charge, so you'll get number of carriers, right? So this is nothing but number of carriers, right, by number of photons we supply. So it is nothing but our optical power input over h nu. So optical here is our optical power by each photon energy, so it will give you number of photons. So it's basically ratio of number of carriers by number of photons, that's all. And the value, it will be definitely, it will have value less than 1. So this is how the range of eta. And then next parameter is responsivity. So the responsivity R, it is defined as the photocurrent whatever we are getting by how much power we are supplying. So this is again optical power, P in. So we write it down. P in is optical power, okay. Input, you can write input optical power, okay. So so it will have an unit of current, ampere by watt. So this is the unit of it, ampere per watt. So how do you define again? So it is IPH by PN. So IPH, how much current it will generate, so it is eta into E over h nu, right? From there you can calculate from here. So IP okay, you can see now. So we know eta equal to IP by E into P in by h nu. So from here we can calculate IP by P in, right? So it will be eta into E by H nu. So just we are rearranging the above equation. So from this equation you can calculate the responsivity of the device. If you can rearrange this with a very popular way of writing is E by HC. So we are basically splitting this nu equal to C by lambda into lambda, and now we can write this we can write this E over HC as 1240, right? Wherein if you put lambda in nanometer, so you can simplify or calculate the responsivity of a device easily if you know the eta or the efficiency of the device and whatever the incidence photon wavelength. Okay, so other two parameter, raise time and signal to noise ratio. I mean it will basically raise time, it will totally depend on your device construction. It's the length of the device and mobility of the carriers and all. It's a complex thing to calculate here. And signal to noise ratio, it defines about so we are talking about photoconductors or photodetectors, right? So in the dark also we'll have some photocurrent. So the dark current by photocurrent, this ratio will give you an idea about signal to noise ratio. So ideally for a photoconductor or a photodetector, the dark current should be as low as possible, right, to get a better signal to noise ratio. So this is just few basic parameters we defined. Now let's talk about okay, where do you start? So you have photodiode, photoresistor, photoconductors. Let's talk about little bit photoconductors and their working principle. So you all know about LDR, so let's see how do they work. So we are talking about now photoconductors. Okay. So in the photoconductor, if you see the device construction, it's a conductor, right? There is no semiconductor junction present in this particular camera is on. Okay, so let's see. So photoconductors, it is there is no PN junction in this type. So if you look at the construction of an LDR or so, similar type of device, so it's a semiconductor material. Let me just draw a simple photoconductor device structure. So we have a it's a semiconductor, usually it's a semiconductor material, and we just have two contacts, just two contacts we have here and on the other side. Now if we bias this one with a resistor, so let's put one load RL and let's connect it with a battery. Okay, so we have battery positive negative, so this is our current flow direction. Now we can take the output across this RL. So this is our V0. So how this device works is very pretty simple. So it's a semiconductor material, and most of the time we use what is that LDR we use? Remember the material we use in LDR? It's a cadmium sulfide. So just to name it, it's cadmium sulfide. So S it is CDS. Cadmium sulfide we use in our regular LDRs, which which has a maximum lambda peak, the absorption around 600 560 to 600 nanometer. So it's come in the visible region. 600 nanometer. I don't remember exact the band gap of this material, but you can guess it. So this is its peak absorption wavelength. Okay, so how does it work? So in the dark condition, so this is just a semiconductor, and it has of course a few electrons and hole present in it. So there will be thermally generated electron and hole pairs. So it has a conductivity, but now the situation when photon falls over this semiconductor, and if the photon's energy is greater than the band gap of the semiconductor, so for this particular cadmium sulfide it comes around this wavelength. So these photons will get absorbed in the semiconductor and it will create electron and hole pair. Now so we have an electric field here, right? So plus to minus, so we have electric field in this direction across this semiconductor. So the electron will go opposite to the electric field and holes will go towards the electric field, right? So the electron will move okay. So we have electron hole pair generation. Hole will move this direction and the electrons will move in this direction because the electric field is in this direction. Now we have basically excess carrier generation within the semiconductor. So all we know, if there is an excess carrier, the conductivity of this device will increase, the resistance will drop, so the voltage across V0 it will decrease, right? So they are in series, so it's a potential divider circuit, and you can keep on monitoring this V0 and you can calibrate the device with photon flux, right? So if this phi increases, the V0 will reduce, right, or increase. If photon flux increases, the resistance of this device or this photoconductor will reduce, so the drop will increase, right, not decrease, it will increase. So you can detect basically photons, and in the dark condition, so this will have very high resistance, it will have very high resistance, so the current will be very less across this circuit, so our V0 will be low. Now as photon falls on the device, we'll have excess carrier, excess electron hole pairs, they will increase the conductivity of the device, hence the current, and the output voltage also will change here, and we can use it as a sensor or a photoconductive device. So these are used in where we don't need very fast, or response time, we don't need very high response time, or very fast response we don't need, we use LDRs. And again, to reduce this transit time, so the response time will depend on the device length, right? Here the device length, if it is L, so I'll just give you the concept of it, why we go for this interdigited electrode. So the length is L. Now suppose a photons got absorbed in this position, this particular position, and the electron hole pair will generate locally, right? So now to observe or capture this carriers, it need to travel, right? So the electron has to reach this electrode, the holes has to reach this electrode, so it has a transit time, and because of that transit time the device response will be slower. Now if you can reduce this L, you can have a better response time or a fast device. So to do that, we go for this interdigited electrode. That's why in LDR, if you look at very carefully, you'll see the electrodes are something like this. So this is our one electrode, and this is the another electrode. So it is basically painted on the electrodes are painted on top of this semiconductor material. So this is our semiconductor material. So on top you basically paint this kind of electrode. So it will improve two way. One way is the electric field will be high, right, because the electrode distance now reduced enormously, and also the transit time is very less. The electron can quickly reach to this electrode, or hole can reach quickly to this electrode. So we can improve the response time, and also transit time we can reduce drastically by going interdigited electrode. And if you want to draw its IV characteristics of this particular device, it's very simple. So let's quickly draw the IV characteristics of this device. Voltage, and this direction we have the current. So when there is no photons falling on it in the dark condition, so initially when you start applying, so we are now doing IV characteristics. Basically we are varying this voltage, right? Whatever the V voltage we are applying, we are varying it now. So we are starting from 0, sweeping it, and you will see after some time it will saturate, right? The current will saturate because whatever the thermally generated carriers are there, you are using all of them. So it will saturate, and if you apply the voltage other way, negative potential, so it will be exactly mirror image. Because it's not a PN junction, there is no directionality here, so it will follow exactly similar thing. So here it is at dark. Now suppose if you launch some photons on the device, so again we'll have excess carriers, so we have more carriers now. So now the saturation current will increase, but again it will saturate if you keep applying the voltage. So again in the other direction also it will follow the similar trend. So this is phi 1, and if you keep increasing this phi 1, this saturation current will keep on increasing to some extent. Yeah. So this is how it's typical IV characteristics of a photoconductor.
What is phi, sir?
Phi is the photon flux. Yeah.
Okay.
Yeah, it's a photon flux. So flux density you can call. So phi equals to 0, we are basically drawing this one, the first curve. This is for dark condition, and then we have under the light. Now if you keep increasing the light intensity, you'll get another curve on top of it. So phi 2 is again greater than phi 1, and it will repeat the same in the other half. Okay, so this is photoconductor. We are not going much deep into, so there are calculation. If you want to learn this, want to calculate its transit time and all, you can follow the book, but we are not going very deep into all these mathematical derivations. We're just learning the working principle and basics design of the device. So let's talk about another device. Sorry, any doubts?
Yes, sir. Sir, one small thing, sir.
Yes.
Here we are going towards the integrated electrode structure because there will be an effective collection of this electron holes at the respective electrodes compared to the bulk scenario.
Yeah, Vikrant, can you repeat once again?
We are preferring this integrated electrode structure.
It is called IDE. It is interdigited electrode. Yeah, I'll just write down. Yes, go ahead.
Okay, this one we are using because there will be an effective collection of this electron hole at the respective electrodes compared
Right.
to the previous scenario.
Yes, from here, right.
Yes, sir. So that's how the field is more.
Yes. So field is more, and also the transit time of the carrier, if you see, the electron has to travel all the way the device, right? Now the electron can be collected very nearby electrode. So the transit time also reduced drastically for the carriers. So 2A, we are improving the device performance by going ID. One is high electric field, and also the transit time, lower transit time.
Fine, sir. Thank you, sir.
Yeah, so it's called interdigited electrode. We use it, even interdigited capacitors also used to increase the surface area of the capacitor. Okay, so let's go and see photodiodes. Okay, I'll take a new board. Sorry, photodiode only. So now let's talk about photodiode. So a regular photodiode is nothing, a PN junction, again PN junction, it's a PN junction only. So we have PN, and now it's a diode, right? So we have directionality and also depletion region. We'll see that. So regular photodiode, usually we bias it in reverse bias. We'll come to that why in reverse bias. So we bias it in reverse condition. So we connect N to positive and P to negative. So in this reverse bias condition, what will be the depletion region? It will be more, right? So let me draw the depletion region also. This is the depletion region, it's much wider. Okay, so P type, so it's we have the acceptor ions, right? So we have all the negative ions here, right? And N type, so it's a donor, immobile donor ions, they are sitting here. So we have basically one inbuilt electric field, and also we are applying externally this reverse bias voltage, right? So because of that also we have another electric field across this junction. This, I'm talking about this metallurgical junction, this depletion region. So we have basically very high electric field across this junction. Now in this device, if you keep it in dark, so only the dark current or the reverse saturation current will flow into this device, right? The reverse saturation current, whatever, it's a PN junction diode, so it will be very similar to the situation we studied as a PN junction diode. Yeah. So you remember the dark current for a diode. If you write it as ID is our IS, so reverse saturation current. Okay, I'm writing about the total diode current. So ID is IS into e to the power EV by KT, just to remind you, minus 1. And if the diode is not an ideal diode, so we'll have an non-ideality factor eta here, right? So this is our regular diode equation, and in the dark the current is, so the V is negative here and this factor. So in dark situation, in reverse bias condition, we are not talking about photons yet, we are just discussing the basics of diode first. So the V is negative, and in reverse bias condition, so the voltage, if it is if you see this factor, it will go almost negligible. So the reverse saturation current will be just simply IS or minus IS, right? If you neglect this quantity for reverse bias condition. Now for this diode, if some photon falls into this particular junction inside the depletion region. So some photons falls in the depletion region. So what will happen? So if the photon energy, again when you talk about photon, you have to talk about energy and the band gap. If the energy of the photon is higher than the band gap of this semiconductor, then the photon will get absorbed. Again it will create electron and hole pairs, and so let's say it has created one electron and hole pair here. Now this electron and hole pair will feel this electric field, right? So the electron will move this direction and hole will move towards the field direction, right? So basically we will have one current flowing now. So we had this reverse saturation current Is, and now we have excess current because of this generation of these carriers. So this current, if we define as photocurrent or IPH, so the total diode current, or so total diode current, if you define it under photons, so it will be then minus Is minus IPH. So this photocurrent will be added to your reverse saturation current. I mean, the working principle is very simple. Now this diode, the diode current will be controlled, or it will vary according to this IPH. So, and this IPH is totally depend on the photon flux density, right? So whatever the flux phi we are launching in this junction, so it will totally depend on that, and so we can basically calibrate the diode, or we can have an idea of photon intensity by just calculating this current. So in ideal situation, we don't connect the diode directly to the battery. We use a resistor actually. So let me just put the resistor here. So we put a resistor across, and then only we connect. Otherwise you will burn the diode, right? If this voltage is higher than this reverse background voltage, the diode will break the junction otherwise. And then we basically measure the voltage here. Yeah, so this will be the V0. So we can calibrate this, and if you try to draw the IV characteristics of this device, so let's try to draw the IV characteristics. But first of all, you understood the concept. Okay, so one more thing, why not in forward bias? Anyone can guess in forward bias? Will this device will work in forward bias if you do so?
Forward bias depletion region will decrease, and number of electron and hole pair generation will be very small, so we get very small photocurrents.
Right. Yeah, and yeah, perfect. And one more thing, in forward bias, this current, diode current will be much higher, right? In reverse bias, the Is is very less. If you see the order of magnitude of Is and IPH, so Is is around microamp, nanoamps. It's a very good diode, you will get in nanoamps, and IPH generally you get in milliamps. So you can see the change from dark to under photon. Change is huge. Now in case of forward bias, the diode current will be itself in milliampere or even amperes, right, in forward bias. So this is, we are talking about reverse bias, and in forward bias, so the order of diode current, it's order of milliamp to amperes, and your photocurrent will be even less, right? As you said, the depletion region width will be reduced when you do a forward bias. Yes, so it will reduce your photocurrent. So maybe it is even if it is still in milliampere, you can see the difference between them. If you want to take a ratio of these two, it will not be much, there will not be much change. So that's what the signal to noise ratio, if you want to calculate, will be very poor in this forward bias, whereas in reverse bias is huge. It's in nanoampere to milliampere, almost 10 to the power 6 order of change. So it's very sensitive to photon in reverse bias. I mean, the current is very sensitive to the photon flux density in reverse bias. Okay, so let's draw the IV characteristics. Okay, let's try to understand IV characteristics. So in the dark, you can easily draw it, right? In the dark, it's like a normal PN junction diode. So let's draw it. So you have voltage and current. So let's draw forward and reverse both. So in forward, we are in this quadrant, right? First quadrant. So forward bias diode IV, initially it's very low, then when we cross the knee voltage, it increases exponentially, right? And then in the reverse bias, so it starts with very low and then it saturates with our IS. Oops. And they are not in scale, right? Okay. So this is our minus B reverse bias. So this scale will be in microamps or even nanoamps, and this scale is in milliamp or in ampere. So the scale is not same. If you really do an IV characteristic on the same scale, you will almost see nothing in this third quadrant. So we generally use different scales to plot them. Okay, so this is at phi equals to 0, that is in dark condition. Now let's see, we have a photon flux. So some photons are falling on this metallurgical junction or within the depletion region. So what will happen if you see the diode equation? So we have we plotted this, and one IPH will be added to this. This photocurrent will be added to our diode current, right? So the curve will basically just shift across this y axis, or across the y axis. So let's try to draw it. It will just shift across this y axis, and ideally if you want to draw this separation will be very high. Not drawing on the scale, but ideally it will be very high, this separation. I'll just draw a typical one, and then furthermore, okay, so this 0 point will be a little bit complicated. I mean, it's not as I draw, it's a very continuous straight line, and there will be this knee voltage and all. You will be able to see that, but for simplicity I'm not drawing it, just showing you the shift along the y-axis. So this shift will be our IPH amount. So I have drawn 3 of them. So one is phi equals to 0, and this one for let's say phi 1, and this one let's say phi 2. So it's the order is like this. So if you keep increasing the photon flux, the IPH or the photo generated current will increase and the curve will shift towards down, right? So for a particular voltage you can okay, so for a particular voltage, if you keep the biasing voltage, so we are again using reverse bias only, right? So if you keep the reverse bias voltage fixed to a, let's say, minus X voltage, then you can monitor this current. You can see the diode current is changing. You can see this diode current changing, or you can monitor the voltage, corresponding voltage also will vary across the load, right? So you can monitor the photon flux density through this device. Now in this we are fine, but there is a problem, like the sensitivity of the device is totally depend on this area, this depletion region area. So for a diode, I mean, we can tune it, we can increase the reverse bias voltage and get a wider depletion region so that we can capture more photons, but it is limited to some extent, right? We cannot have very high reverse bias voltage, will break the junction, right? So to increase the sensitivity of the device further, there is another concept of the same diode. It's a again PN junction diode, but we will just modify it. So let's go to that. Much more efficient construction could be like this. So let me draw the device, then you will agree with me. Okay. So we have P, N, and I'll put one intrinsic semiconductor in between. Now let's bias the same way and see how this will help us to capture more photons. Again, reverse bias. Okay, let's put a load here. Okay, so this is our RL, and we'll measure the voltage here. So in this construction, again it's so this is called pin photodiode. So we are now into pin. Photodiode. Okay, so this is okay. So P side we have P-type semiconductor, then we have an intrinsic semiconductor, and then N-type semiconductor. Now what's special about it? So the whole I region or the intrinsic semiconductor will be as if behave like a depletion region. So whatever the carrier, whatever the photons falls into this I region, it will generate this EH pair, right? And they are under electric field, right? So they are under electric field and they will get swept apart as before. So the electron will move towards this positive N side and hole will move to this P side, right? So this plus minus, the electric field is in this direction. Yes, so electron will go towards the N region and holes will go towards the P region, and the device working is very similar. So at dark we'll have only the dark current, and when there is a in the presence of photons, it will create this EH pairs in this whole I region is now our active region, and they will get collected to this device, right? So we are basically increasing the device sensitivity, or the capture area is more, right? So the device will be more sensitive to the photons in this construction. So okay, let me just try to draw the electric field distribution once. You want to see, let's try to see. Oops. So we're trying to see the electric field distribution. So this is our X, and this is the electric field E. So the electric field at this electrode, it is 0, right? And now the field will be maximum. So okay, so this is minus Electric field direction is this way. In PIN photodiode, generally we use this P side as heavily doped, or yeah, we use heavily doped P side for a PIN photodiode. Yes. So on at the electrode, the electric field is 0, and then it will increase. And now in the intrinsic region, so there will be some voltage drop across this intrinsic region, right? But it will not be too much. So it will gradually decrease to some extent, the slope, okay, something like this, and then again at this electrode the electric field will be 0, right? So this is the variation of electric field across the device. We'll have maximum electric field in this junction, and then it will reduce like this. I think it will be other way, right? So P is positive, so electric field direction, yeah, actually it is minus E, because see, battery positive terminal is here, right? So the electric field direction will be negative. The way I drawn it should be flipped, but anyway the variation will be like this. So so whatever the electron, why I drawn this picture is to show you this electron and hole pairs, they will be under this electric field. So there is already electric field present here, even in the pin region, in the intrinsic region also there is a electric field. So because of that field, the electron and hole pairs, they will get separated out and they will contribute to the photocurrent, and the device will work. I mean, so the idea is increasing the area of this device. But the problem also here persists, like we don't have a gain here, right? So we are getting just each photon at maximum we will get one electron and hole pair. We cannot get more than one, right? It will be less, in fact. Not all photons will generate electron and hole pair, and even if they generate, not all of them will contribute. Some of them will recombine within this region itself. So we don't have a gain, but definitely we can sense the number, we can sense the photons presence or the flux density. But if you want to have a gain or a better signal to noise ratio in this structure, not possible, because the number of photons is 5 by h nu, and number of carriers it is generated, so IPH by E. So our number of carriers is always less than number of photons in this kind of device, all photodiodes or even the PIN photodiode. Now, can you have some gain in this kind of device? So that's what the next level of next generation of detector comes in, what is called Avalanche photodiode. So let's get into the Avalanche photodiode, which is called APD. So first I will just draw a basic APD. We'll see the problem and then we'll go to the advanced one. So a basic APD is nothing but again PN junction diode, and this PN junction diode, we make it very heavily doped. Both are heavily doped. So we are talking about now APD, Avalanche photodiode. So we moved from PIN to APD to have some gain. So let's see how we can have some gain in this device. So again, it's negative reverse bias, right? Okay, so we should always connect a load whenever we draw with diode battery. So now in APD we use very heavily doped PN junction. both of them, P and N, are heavily doped. That's what the plus symbol signifies, right? It could be even degenerate semiconductor. Now, by going for this heavily doped, what will happen is our junction area, the depletion width will be very narrow, right? We all know if we dope heavily, the depletion width reduces, right? So in this construction, whatever the VR, if we keep increasing this value of VR, the reverse bias potential, then so again it will generate this electron and hole pairs in this junction. Now if you make this device thin, this P and N, the size is narrow, so we can basically create an enormous electric field across this device. And if the electric field is very high, so in APD we generally create electric field of the order of 10 to the power 5 volt per centimeter. So this is the order of electric field we create across the junction in case of an APD. So with this high electric field, what will happen? So this electron will move towards this side, right, and the hole will move towards this side. So while the electron is moving into this N region or this N plus region, so it is under very high electric field, so it will accelerate very fast and it will acquire very high kinetic energy, right, because of this high field. So if the kinetic energy is sufficient enough, it can knock out another electron from the atoms present in this N region. So N regions we have again other semiconductor atoms, right? So if the energy of this electron is this photogenerated electrons is very high, it can knock out another electron from this atom itself. So it can ionize this atom and it can create an electron hole pair here, somewhere here, and then again this electron will accelerate in this direction, hole will accelerate in the other direction. So now we will have two electrons here, right, in this position. So let me draw a bigger scenario. So we are basically a little away from the junction. We're talking let's say so this is the metallurgical junction, okay, and we have the depletion region here. So we got an electron and hole pair and the electron is accelerating in this direction and it has a sufficient kinetic energy to achieve because of this high electric field, and now it will knock out one electron from this device. So it will create one electron and hole pair in this position. So we'll have now one electron extra and the same electron will continue. So we'll have two electrons in this position, and this electron and both of the electrons, they will keep accelerating along this direction. The hole will start accelerate in the other direction, right? Now this two electron again can create, there is a possibility it can create again one more electron hole pair, right? So again it will have here two electron, one extra will create, so this two will again accelerate, this two electron will again accelerate. Like this we can have this process continues. So this is called avalanche process, and this kind of ionization is called impact ionization, impact ionization. This phenomenon is called impact ionization. So because of the high electric field, the electron can knock out another electron present in this device, and it will have a gain. Now you see that we have started with just one electron and hole pair. Now this electron is generating, multiple of electrons, and this process will continue and will have a huge photocurrent in this device. Similarly, the other half, if you consider, the hole also can do the same thing. It can also accelerate. Definitely hole has lower mobility in most of the semiconductor compared to electron, so it might not be that much efficient as electron, but it can also knock out the same way, and the multiplication process can continue. So from here also some electron will come off, right? Because whatever the holes is generating here, so few electrons will again come from other end also. So this process will continue. If you see that we started with just one electron and hole pair, and the process is almost endless. I mean, if you see this way, it's almost endless, right? So this cell will accelerate, it will reach to the p side, and this electron and this hole can create again EH pair. This electron will again take part, right? It will take some time to transit other region, and this process will keep on going, but practically it will not go for long time. Definitely it will die off maybe in few seconds. But you understood the concept of impact ionization. This device has a problem. Like as I said, this process may continue for longer than the signal present. So let's say we have a burst signal at the input. We have a optical burst signal. If you say this is with time and the photon flux. Now, if you in the output we are measuring just voltage, right? So okay, we'll get a burst, but now this process will continue for some time. The output voltage V0 across this RL because of this multiplication, right? So our input signal, it was just a very short burst signal, and we got a very broad signal. So there is a device construction wise, there is a problem in this construction, because of this multiplication process is continuing longer than the signal present. So we can improve on this device structure. So that's where comes our another type of APD. It's called reach through avalanche photodiode. I'll just briefly go through this reach through photodiode. It will take a little time to understand the concept, but I think 15 minutes. Okay, we'll just quickly go through. So APD, you understood the advantage from normal PN junction, right? We have gain here, so we don't need to attach a pre-amplifier, because in photodiode or in the case of photoconductor, the amount of current we gain in milliamperes, so we cannot directly, or sometimes in microamperes, so we cannot use this current, or we cannot carry the signal long distance. So generally we have a pre-amplifier attached to the device very next to it, and then amplify and take the signal out because of the weak signal. But in APD we have gain inbuilt in the device, so we don't need to attach a pre-amplifier with APD because of the high gain. So but the problem is again this signal persistent. It is, we're getting broad signal with this type of construction. So that's why the people or the scientists, they have come up with a
typical value, sir.
Typical value of
Current improvement in the current compared to a normal.
So yes, so this is called multiplication factor. So whatever the impact ionization, because of that we're getting, it's called let's discuss that part first. So we're getting, it's called multiplication factor, because you can see that our carriers are getting multiplied, right? It's also called the gain of the device, and gain of the device, and it is denoted with the symbol M. So it is defined as multiplied photocurrent just use shortcut, and then by primary unmultiplied photocurrent. Unmultiplied photocurrent. So as you can see, it's multiplied photocurrent in the sense when this photomultiplication process is taking place, we have applied a quite high reverse bias voltage so that the multiplication process has started. So we have applied sufficient electric field to this impact ionization process start with. It should start this impact ionization. So it has a threshold electric field we need. So we cross that, then we get this multiplied photocurrent. And primary unmultiplied photocurrent is that you apply a lower voltage so that this process doesn't start, this impact ionization. So you'll get a very low current, and the ratio between these two will give you multiplication factor. It is written as IPH, but IPHO. O in the sense it's in this unmultiplied one, very low field. So the value could be somewhere around, so this is where your answer goes. So it's around 1000 for a regular APD we use. Sometimes even goes to 10k also, 1000 to 10k. So we have this amount of gain or multiplication factor within the device itself. And mathematically it is, if you do math, they empirically found like this. So it goes with 1 over 1 minus VR by VBR to the power m. So let me define what is VR. So VR is the reverse bias voltage what we are applying. So I think I used capital R, is it? Okay, doesn't matter. So this is reverse bias voltage, and then VBR is the breakdown voltage of the junction. It's the avalanche, sorry, it's the avalanche breakdown voltage. Avalanche, CH, one H is there, HE, avalanche breakdown voltage. Okay, and so we have one factor m we didn't define. So this m is called characteristics index. So this provide basically the best fit to the experimental data. So I'll just explain how we get this characteristic. It's called characteristic index. So you can see the value of m. Now to find this m we need to do an experiment. So we know the breakdown voltage, avalanche breakdown for this device, and then we calculate, and we basically do multiple experiment with different reverse bias voltage. So different reverse bias voltage, you will get different multiplication factor. This is constant for this particular device construction. Now if you fit into this equation, so you'll have a set of VR, set of reverse bias voltage with different multiplication factor, and if you fit that curve into this equation, you can calculate this value of m. So this will give you the characteristics index of that device. And this is the manufacturer, they will give you this value of VR, value of m, characteristics index. Now for your experiment or for your requirement, you apply whatever the multiplication factor you want. You can back calculate the reverse bias voltage you need for the device. So it's an important parameter. Yeah. So it's typically 1000 to 10,000 it lies in the multiplication factor. I think we should stop.